So good morning. Now, our main goal today, and we're going to look at lots of different examples. Our main goal today is what's called sampling. Now, statistics is about data collection and what to do with the data, and then how to make conclusions about the data. Okay, so we talked about that last time, data, same word. And I've got all of this information, maybe I've collected from the population, maybe it's a census, maybe it's, I polled everybody at Mesa College and asked them a question. I've got all of this information. So the number crunching and the calculation comes a little bit later. The making the conclusion about that, that's a really important thing. The question is today, how do I actually collect the information? Now, this is really, really important. And I'm going to go back to the same example over and over again during the first few weeks, because it's really simple to comprehend. And that is, I would like to know what is the average height of a Mesa College student. Now, we have tens of thousands of students. So how would I collect this information? So for example, I would like to find the average height of a Mesa College student. So what I'm going to do is I'm going to select Rosalind. I'm going to measure your height, and I'm going to use that as the example of the average height of a Mesa College student. Do you think this is a good idea, considering there's about 25,000 Mesa College students? Do you think that's a very good way of, right off the bat, I'm going to pick one person and they're going to represent the whole campus? Anybody? Do you think that's an effective, accurate measure?
No.
You can say no. Probably not a great idea. What would be a better idea than to pick one person and have them represent the whole campus?
Like a sample of people?
Well, a bunch of people. Okay, good.
A bunch of people?
Right off the bat, you say, a sample of size 1 probably isn't.
True.
Yeah, I want to know what people thought about a movie. Maybe some big blockbuster just came out, and I would like to know what Americans think about the movie. So I'm going to ask the first person I see, did you like the movie, yes or no? And I'm going to make my conclusion about the United States of America by asking one person. No, that's probably not effective. I probably want to ask lots of people. So first of all, asking lots of people or collecting lots of data is better than only a little bit. So when it comes to sampling, the bigger the sample is always better. The more information you have, it's always better. The more likely you're going to be right. Okay, so I would like to collect a sample. Now we're going to talk about the different forms of sampling, and the very first one is what's called a random sample. And the word random is extremely important. Now, I can have a random sample of size 1. I can have a random sample of any size. Okay, the size of the sample is predetermined. Now, it might be something like this. We're going to have a lottery, and there's only going to be one winner of the lottery. Okay, and the lottery is just going to be the students in this class. So cool, I have a better chance of winning because there's not that many people. We have a lottery of size 1. Do I get to pick the winner? Is that a fair sampling if I get to pick the winner? If I choose who's going to win? No, that's not much of a lottery, is it? So the first thing is, in a random sample, the most important part is that every single person or whatever you're sampling from is equally likely to be selected. This is huge. So if I'm going to do a random sample of people, that means every single person is equally likely to be selected. Now, whether I select one person, 3 people, 10 people, that's not the question of how many. It's that no matter who is selected or how many people are selected, everybody has exactly the same opportunity. That is absolutely critical, because if one person is more likely to be selected than another, then we'd say there's bias. And we used that term last day. Okay, and you could just simply argue, well, that's not fair. I didn't have a chance of being selected. So I want to do a random sample of size 1. I want to pick one person in this class to be the winner of the lottery. Now, there's many ways I can do it, but probably the simplest way you could even think of. Anybody want to try this one? Just what would be the simplest way to select one person in this class where everybody's equally likely to be selected? It's probably the oldest method that exists. You may have done this even when you're kids.
Write everyone's name on a piece of paper and select it from a hat.
Perfect answer. That is it. That's it. That is the simplest and at the same time most accurate and most fair way of doing this. We've got a small class, we write everybody's name on a piece of paper and put it in a place where you can't see the names and somebody reaches in and grabs a name. And most of you have been in a situation like that. You said, that's brilliant, that's so simple. But it only worked because our population was really small. Suppose I wanted to select people from San Diego County. Now, maybe I'm going to use a phone book now. Could you imagine taking the phone book and cutting every individual name out and then putting them all in a hat? Now we'd probably have a few 100,000. That may be less practical. It's still going to be fair. It's still going to be accurate. But the name in the hat and selecting one is the ultimate simple way of doing what's called a random sample. Now, there's two types of random samples I just said. One where I'm going to choose one, or one where I'm going to choose a pre-selected number. So maybe I'm going to say, you know what? We have a lottery and we're going to have 3 winners. So we do the exact same thing. We put the names in a hat, mix them up, don't look at them, and we pull out a name, we pull out a name, we pull out a name. If I pull out a name and I read that name, should I put the name back in the hat, or should I remove it from the hat? Or does that really matter?
You should keep it in the hat, because then the likelihood of the people after winning is greater.
Well, so in other words, you're saying if I put the name back in the hat, but then can't I pick them again?
Yeah, but then you just keep going until you found another one.
Oh, okay. So if I pick them again, I just ignore it. Is that what you mean?
Yeah.
We could do that. Mathematically, believe it or not, putting the name back in the hat mathematically is actually more accurate. Or you can just say, I'm going to reach in the hat and grab 3 names at one time. That would be a fair way of doing it too. So a random sample. And by the way, anytime we do a sampling in any situation, you would like to know that every person is equally likely to be selected. Okay, that's really, really important. I'm going to do a random sampling of books on my bookshelf. Then what I would want to do is probably write down the names of the books, put them in the hat. You know, don't put the books in the hat. That's too many books. They're too heavy. But everybody's equally likely to be selected. So now we're going to start this process. We would like to sample from Mesa College. And let's make it really simple. We want a random sample of size, and we always use the letter N. So we'd say N equals 100. I think if we had 100 people, that would probably be a good start. Again, we agree that with 25,000 students, picking one person is probably not a good representation, because what if that one person was really tall? What if that one person was really short and they're going to represent the entire campus? You don't know that the one person is going to be the perfect height to represent. So you'd say, let me pick a bunch of people. 100 is a good start. 1,000, that would be better, but that could take a really long time, perhaps. So let's pretend one thing. Let's pretend we're actually back on campus, because I've done this example for 1,000,000 years. So we're back on campus. So there's thousands of people buzzing around campus. Okay. Now, if you say, I'm going to pick that person, I'm going to pick that person, I'm going to pick that person, and you start selecting ahead of time who you're going to pick, that could be a little bit biased, because again, everybody should be equally likely to be selected. So what some people do, they'll say, I will station myself on campus. I'm just going to put myself in a particular place, and the next person that walks in that door, or the next person that walks out of that door, because I have no control over that, I will ask that person, I would like you in my sample. That's not a bad way of doing things. So I'm going to throw some ideas at you, and you're going to get back to me. Okay, so I would like to randomly select 100 Mesa College students. And remember, we want everybody to be equally likely to be selected. Now, it's Tuesday morning. It is about 7:30-ish. And right now, you're positioning yourself on campus, and you're going to ask 100 people. So maybe you're going to be over by the cafeteria, and you're going to ask the first 100 people that you see, and they're going to represent Mesa College. Is this a fair random sample? Again, Tuesday morning, well, technically today's Thursday morning. So Thursday morning, 7:30, you're outside the cafeteria, and you're going to ask 100 strangers. You're not going to pre-select them. The first 100 people you see, you're going to ask. And you're going to say, can I measure you? You're going to measure their height. Assume they're going to say yes. And you're going to measure their height, and then that's going to be our random sample. Remember, the idea of a random sample is that every single person is equally likely to be selected. And because you're not going to pre-select anybody, People are just gonna walk by, you're gonna say, does anybody think this is a good way? It's a start, certainly, but is there any flaw with this? Thursday morning, 7:30, you're measuring.
Professor,
What do you
I
think?
would first say it is a good method, except for because it's at 7 and maybe not everyone has classes that early.
Okay, good. That's the first thing that's wrong with this method, is that I'm excluding everybody who starts later, aren't I? Now, let's go back up. So you're absolutely correct. That is a flaw. Only people who have class at 7:30 on Thursday morning are likely to be selected. You guys have class Tuesday, Thursday. Most Mesa College students, my experience is they're either Monday, Wednesday students or they're Tuesday, Thursday. Not a very high percentage of students go every day. Most of us try to get all of our classes in 2 days. So if I'm doing this on Thursday morning, you said I'm excluding people who start later in the day. Who else am I excluding on Thursday morning? Anybody? You are all Tuesday, Thursday students, right?
Monday, Wednesday students.
I'm excluding the Monday, Wednesday folk. Ooh, by the way, most of my Monday, Wednesday people, I teach linear algebra and Calc 3 on Monday, Wednesday. Those are high level classes. Only the students who have physics have Tuesday, Thursday classes. Every one of my Monday, Wednesday students are exclusively Monday, Wednesday. Okay, so now we found two major flaws with doing the 100 random people at 7:30 a.m. is that I'm not going to include people who start later. And I'm also not going to include people who are here Monday, Wednesday. Oh boy. Okay, so now, so rather than you individually are going to measure everybody, maybe you get people to help you. Okay, maybe you get people to help you. And so now you're saying, you know what? I'm going to ask a few people at 7:30, but then maybe I'm going to ask a few people at 8:30, and then at 9:30, and then at 10:30. And I do this all the way up till noon. This is better. We all agree this is better. Is it a fix? Is it a complete fix?
No, it's not.
Why not? Again, who are we excluding? Who doesn't have a chance of being selected if we go up till noon?
The people in the afternoon.
Or even evening. You do realize there's an entire population at Mesa College that there are evening students. There's a population of students who only take classes in the evening and take classes in the evening every semester because they work all day, they come at night. Oh my gosh, you mean I gotta be here all day? Well, I have to have people asking the question all day. So now let's go from 7:30 maybe till 7:30 at night. Okay, now we're gonna hit everybody throughout the course of the day. And we're gonna do it also on Monday, Wednesday. Great. So we're gonna stand outside the cafeteria and we're gonna ask people every hour, every day of the week, basically, from outside the cafeteria. Flaws, or is it perfect?
There's still flaws.
Still flaws.
There's still one major flaw here.
Yes.
I've been at Mesa College for 36 years. I have never even stepped inside the cafeteria at Mesa College in 36 years, just so you know. I bring food every day. I've never stepped foot inside the cafeteria. You might find that hard to believe. So I'm not going to be selected because I don't go into the cafeteria. Oh, so do you see the flaw there about positioning yourself in one place on campus? So now, okay, you guys help me out here because we want to get this right. We want to be accurate. We want our sample to be representative. So now you've told me we need multiple times per day. That's correct. We need multiple days of the week. So we do not exclude people who come on the other days or the other times. And we're going to do everything from the cafeteria. Help me out here. What else can we do to improve this?
We can position someone by the LRC or at the bottom parking.
Okay, now
It
maybe
helps.
multiple places on campus. Okay, you guys see how complicated this is becoming? Oh my gosh, I just want to, measure the people, but I want to be correct. If I only stand outside the cafeteria, then I'm only going to ask people who use the cafeteria. And some of you may never use the cafeteria, or may some of you use it all the time, and then you got excluded. So days of the week, times per day, locations on campus. Okay, so I'm a young 20 something and I'm asking people their height, but you know, I have some ulterior motives in mind. So what I'm going to do is I'm going to ask every beautiful woman that I see walk by, I'm going to ask how tall they are, or ask them to measure their height. So I collected my sample of size 100. I collected a sample of size 100 beautiful women.
Bias.
Why? Well, first of all, Mesa is not an all-women's campus, is it? So, my gosh, I probably should have a roughly equal mix of male and female. Do you think?
Yes.
Yeah, because otherwise I will overrepresent. Now we're going to talk about that one. That's the more complicated version. But again, random sampling. Now, here's the thing. If I'm asking a simple question, it could be a political question, you know, who you're going to vote for. Or I could be asking a question, do you approve of Mesa raising the fees? Or I could ask a question, are you a full-time student, yes or no? If it's random, male, female, age groups, those things may or may not matter, or those may be actually the most important things that matter. So we're gonna discuss that aspect in a moment, because that's a more complicated thing that again we have to take into account. So again, multiple days of the week, multiple times a day, multiple locations on campus, and I'm not pre-selecting people. I go, oh, I want to ask that person. I don't want to ask that person. Right now, you guys have just made huge leaps and bounds. The sample you collect now is far more likely to be representative, okay? Far more likely to be representative of the campus. Can it still go wrong?
Yes.
Yeah, it can always go wrong in that it could still be biased in one direction. So I'm trying to be fair. So I'm doing the cafeteria thing, and the next 10 people that I ask all happen to play on the basketball team. Just random chance. The next 10 people I ask are all on the basketball team. Tell me about my sample. What's it going to look like? Do you think it's going to be really, really accurate, or maybe it might be a little bit tall?
And it could be, if we use this method, it could be very inconsistent.
Yeah, if I basically include the basketball team in my sample, and the basketball players tend to be a little taller than the rest of everybody else, I might be a little bit biased. Now, is this a possibility in any fair sample? Yes, it is. It's a small chance that you just happen to have the tallest people on campus, or it could be that I just randomly asked everybody who is a hobbit, you know, and I got all these 3-foot tall people in my sample. But generally speaking, if we are unbiased and we do it properly, the sampling properly, it's going to far more likely to be accurate. So I'm giving you some ideas of how sampling has to occur. Sampling, again, the number one thing is that every single person is equally likely to be selected. Now, are you individually going to be selected? Well, probably not. I mean, we're only picking 100 people out of 25,000. But everybody's equally likely to be selected. So you could be, you might not be, but that isn't going to affect the accuracy. So now when we talk about things, and we're going to do the mathematics later of this, but we talk about things like opinion polls. Most people, if they don't know any better, don't trust opinion polls for the simple reason that they didn't ask you. Right? They asked perfect strangers, what do you think about an issue? And then they report these numbers. This is what America feels. And you're saying, but they didn't ask me. How do they know that's what Americans feel like? Well, if they did their sampling correctly, and it's a random sample and everyone's equally likely to be selected, then the people they selected are probably not going to be too far off of what the national opinion is of that thing. Believe it or not, we're going to discuss the mathematics of that. That's closer to the middle of the class. And if you do it right, you really can trust the results. So that's the whole point. We can't ask everybody to be measured. We can't ask everybody their opinion. It just takes way too long. Okay, so we've got all of this. So finally, okay, we've stationed ourselves multiple places on campus, multiple days of the week, multiple times per day. And you have a whole crew of people. And so finally, people come up. So Rosalind walks up and I say, all right, will you be in my sample? And you say, of course I will. And then I say, how tall are you? So I'm going to ask everybody how tall they are.
5'6".
I think we just hit the final nail in the coffin. Am I going to get accurate results if I ask everybody how tall they are?
No, because some people may lie.
I think what we're going to find out is how tall everybody wants to be. If you ask people how tall they are, they might give you an accurate number. They might not. I'll make it even better. I'm going to measure everybody's height, but not in inches. I'm going to measure everybody's height in centimeters. So I'm going to ask you how tall you are in centimeters. And of course, everybody here knows exactly how tall they are in centimeters, right? Or maybe not. I mean, I don't know how tall I am in centimeters. I need a calculator to convert it. So if we're doing this to find the average height of a Mesa College student, you have to measure them. Self-reported statistics, self-reported data is never trustworthy unless you're asking a question of somebody like, are you voting for this person? Or are you happy about, a yes and no question? No, that you can trust. But if you're asking somebody a measurement question, like how tall are you? How much do you weigh? You have to actually do the measurement, because otherwise you're going to get information that may or may not be accurate. It's not even a question of they might lie to you. They simply might not know. So if I asked everybody here, what is your height in centimeters? I really doubt very many people know that off the top of their head, unless you've recently been measured and they actually gave you the number in centimeters. Most of you would know it in inches, and that's a simple mathematical conversion. But if I'm reporting it myself, again, it can tend to be a little less accurate. So random sampling, everybody equally likely. Start with names in a hat when it's small. Otherwise, I've got to do surveys. That's what we're talking about here. You're doing surveys. Now, everybody here, I'm sure, has been asked a question by somebody, either by the phone or just somebody walking. I don't mean they want you to register to vote or they want money from you, but people will just say, hey, I'm doing a poll. Can I ask you a question? That's happened many times with me. And yeah, no problem. There's no harm done. And a lot of times it's just a simple question, or maybe it's just a few questions. Sometimes it's about products. Do you use this product? Because they'd like to know for their own data collection. Now, I want to ask a question about, let's say, simple phone service question. I don't mean cell phones. I mean landlines. I still have a landline. Okay, I'm a traditionalist. And let's say I want to find out what San Diegans think about their phone service. Okay, so in other words, I can use a phone book. Everybody in the phone book has a landline. That's what the phone book is. The phone book isn't cell phones, it's landlines. And so if somebody doesn't have a landline, I don't want to include them in my sample. So if I get the phone book and I use that for sampling, that's great. The problem is the phone book, there's tens of thousands of names in the phone book. So how could we use the phone book and effectively sample? Now this is not an obvious one, but it's actually a really simple one. To effectively sample, and again, everybody equally likely to be selected. I can't select everybody. Like I said, there's tens of thousands of people, but I would like to find out how, what you think of your phone service, maybe. So let's make it simple. Let's say, let me make it really simple. Let's say there are 1 million names. We have a really big phone book. We have 1 million names in the phone book, and I want to select 1,000 for the sample. 1,000 would be 0.1%, by the way. Because 1,000 times 1,000 is 1 million. So I'm 1 in 1,000. That's 0.1%. Okay. I want to select 1/1000th of the people in the phone book. So do I just start randomly going through, and that's probably not a great way of doing it. But what if I did this? What if I start somewhere? Doesn't matter where. I just start with a name. Let's say I start with person number 47. And then I take the person who's the 1,047th person in the phone book, and then the 2,047th person, and I keep doing that. In other words, I count every 1,000th name and I select that person. I would get all the way through the phone book and I would have 1 out of 1,000. Okay, does that make sense, what I just describing? I start with a random person and then I just count every 1,000th person. Would this be random? Would everybody in the phone book be equally likely to be selected if I did that way, if I just counted by thousands? Anybody? What do you think?
No.
Why not?
Because if you're doing everyone, and if you start off with a random number, you're still missing
But
the
if, let's suppose that you are, 375. In other words, not the 1,000, that's your last three digits. You are 375. Maybe you're the 57,000, but you're 375. If I started with 375, then you will be selected. If I start with 376, you won't be. But if the starting number is completely random, then once I choose the starting number, then I count by thousands, then everybody in that group, they're going to be selected. But if I start with a different number, there's a different group that's being selected. Every time I start with a different number, a different group will be selected. But if the starting number is random, I don't pre-select the starting number. I could do the starting number. There's things called random number generators on every computer. I can just, or like a spinning wheel, like the game shows. I can have the numbers 1 through 1,000 and then a spinning wheel, and then wherever it starts. It started at 47. This type of sampling where you randomly select the starting point and then go incrementally like this is actually how sampling is done when the numbers are huge, 1 million people. This is called systematic. Suppose at Mesa College, by the way, we have a data bank at Mesa College of every single student at Mesa College. Now, how are you ordered? You might be ordered by names, alphabetical order for the entire campus. You might be ordered chronologically by birthdays, in other words, age. You might be ordered by your random ID number, but now putting the random ID numbers in an increasing order. There is some organization of all of the people at Mesa College. There's a database of everybody at Mesa College. And let's suppose I want to just randomly select, a number of people at Mesa College, and I want to go through, have the computer randomly select them. Well, I don't say, well, let's start with name number 1, and then we'll count every, whatever, 100 names or whatever you want to use. Because if I start with the first person, then the second and third and fourth people, they had no chance of being selected. I can't choose the starting point. So if the starting point is randomly selected, then before we start, everybody truly is equally likely to be selected. When we put the names in a hat, before we choose a name, every single person is equally likely to be selected. And that's what it means, again, to be a random sample. There's no bias. There's no hidden agenda. I'm saying, I'm going to make sure these certain people get selected. Nope. So a systematic sample, that would be a phone book sample, where I randomly select. Now, there was a show on television. This is way before any of your times. In fact, your parents may or may not even know this one. There was a show called Dialing for Dollars. Has anybody ever heard of that show? By the way, I'm just curious. I've seen it made referenced in movies and other things, but there was a show called Dialing for Dollars. It was actually located from the Bay Area. And what they would do, they would show, it was like in the afternoon, really bad movies every day, B movies. It's like, why would anybody watch a B movie? Because you might win money. And the way the show worked is they took the phone book, and I believe they cut it in groups of 20 names. And then they put it in this gigantic wheel. I mean, somebody went to all the trouble of taking the phone book and 20 names at a time, and thousands of these, and then they put it in a giant wheel. And at the start of every show, they spun a little thing. There were 20 spots, and it would be like 1 from the top, 2 from the top, 3 from the top, 4 from the top, all the way down to 10 from the top, and then it would be 1 from the bottom, 2 from the bottom, 3 from the bottom, up to 10 to the bottom. And what they'd do, they'd start the show and they'd spin the wheel, and it might say 4 from the top. So that's what they did. So that every single commercial break, they would spin this gigantic wheel of phone numbers. They'd reach in, they'd grab one of these clusters of 20 phone numbers, and then they'd find the 4th name from the top, because that was what they pre-selected. In other words, the random starting point was pre-selected. They'd go the 4th name from the top, and then they would call that number live on the show. They'd call that number, and you answered the phone, and they'd say, "What movie are we showing today?" If you knew the answer, you won a certain amount of money. And I don't think it was a lot of money, but it was a certain amount of money. This was one of the most popular shows on television for a while, because if you were watching the show, there was a possibility you were going to get a call and win money. Now, there's thousands and thousands and thousands of people in the phone book. So what's the chances they're going to call you? Probably not great. But the fact is, they would do this at every commercial break. So there'd be dozens of phone calls for every show. And a lot of the phone calls, the people were watching and they'd win. This is, again, a form of systematic sampling. So let me back up. There were 20 names on every cluster of the phone book. They'd do 20 names at a time. They'd randomly select, whether it was top 10 from the top or 10 from the bottom, they'd randomly select a starting point before the show began. Then every time they grabbed one of these clusters of 20, they'd go to exactly that spot. And that's the person that was called. So before the show started every day, every single person in the phone book had an equal chance of being selected. Once they did the 10 from the top or 5 from the bottom, once they did that, then only those people are going to be selected that day. But then the next day it would start over, the next day would start over, and so on. Now, it's a kind of a crazy concept. I don't know that it would fly today, but this show was on the air for years. Okay. Does anybody here know who Janis Joplin is? Say yes or no. Anyway, Janis Joplin.
Yes.
She was a 60s rock and roller, and like everybody in the 60s, she died of a drug overdose, it feels like. But she was very, very famous singer, and one of her most famous songs was "Oh Lord, Won't You Buy Me a Mercedes Benz." Anybody remember that song? It's kind of a funny song, but she makes reference in the song to "Dialing for Dollars is Trying to Find Me." It's pretty funny because that show was so well known around the country that, even though it was just some schlocky B-rated movies, but the fact is that they might call you and you'd win money. So systematic sampling, a randomly selected starting point, and then I just basically count. A systematic sampling, I want you to associate with the phone book. In other words, huge, huge sampling. Now, what if you were at a football stadium? Okay, you went to a football game at a football stadium, and maybe 60,000 people are there. But the team, the home team, they want to do something for the fans. They want to give random giveaways. So they, in their database, have every single seat, and they can randomly select a seat. That would be a good random sampling. Or they may want to say, you know what, we want to give away a lot of prizes, so maybe we want to count every 1,000th seat or something like that. So then they would do the same thing. They would go through and randomly select after randomly selecting the starting point. Again, as long as everybody is equally likely to be selected, that is the most important part of any form of sampling. If one individual or one item or, one dog, if you're randomly selecting dogs, if one is more likely to be selected than another, then it's not random. Okay. Now we're going to do one more. This one is probably the most complicated, but probably the most important. Now, every time you hear political information, by the way, I'm not political in any way. I don't talk politics with anybody. Nobody knows, other than my wife, what my political opinions are. People always think they do. No, they don't. They have no idea. Because I don't talk politics with anybody for the simple reason, the only reason people talk politics is they want to tell you their opinion. And I don't care. But when you're watching the news and they'll say things like, this percentage of nursing moms voted for the candidate, or this percentage of 18 to 20-year-old, and they'll have an ethnic group. They'll get really, really, really specific about something. Or this percent of working stay-at-home dads voted for the candidate. I mean, sometimes you're watching this going, I don't even know how to interpret that. 60% of Americans voted for this candidate. That's more useful to me, not what small percentage of what really, really select group. So a lot of times when they're breaking down the information, you guys know what I'm talking about. They break it down so specific, you can't really tell. So is this good? Is this bad? Does that mean that person won? But when we're doing that, they're trying to tell you we're breaking down the society into smaller groups and then saying, how did that group vote? That's a fairly simple concept. So we want to do a random sample. And let's make this really, really simple. Let's say, I'm going to make the numbers really nice and friendly. So let's say there are 10,000 students at a particular college. Okay, there are 10,000 students at a college. And let's start with, let's say that 5,300 are women, 4,700 are men. And you want a random sample of 100 students. And you're going to ask a question. We're going to keep it really simple. And you might be asking the question, you know, are you happy with the fee structure at our school? Or the question might be something as simple as, did you buy a parking permit this semester? You know, you can ask any question you want. It doesn't even matter. So I'm going to collect a sample of size 100. And let's say in my sample of size 100, I just happen to have, 92 of the people were men and 8 people were women. Do you think that would be a good sample? And 92 men, my sample had 92 men and 8 women. What do you think? Do you think this, and I randomly collected them, I randomly sampled around the campus. Do you think this is gonna, is this a good sample?
No.
Why not?
It's a bias in you.
Tell me something about my campus, my population. There's 10,000 people, 5,300 are women. That means exactly 53% of my campus is women. But only 8% of my sample is women. If I really, really want an accurate result, anybody want to tell me how many women should have been in my sample? Exactly.
53.
53, excellent. Because that would reflect the population. Now we're talking, this is, by the way, the most important type of sampling. This is what is called a stratified. A stratified sample. A stratified sample is one where your sample reflects the population in terms of categories, if categories are important. So a lot of times we'll say, again, let's keep it really simple. There's an opinion that I want to measure, and I believe that men and women may have different opinions on this topic. So it's really important that my sample reflects the population in terms of the percentages of people. If, let's make it really simple, what if exactly half the campus was men and exactly half the campus was women? Then shouldn't my sample be exactly half of my sample are men and women? That would make sense. Okay, I mean, that would just make perfect sense. So a stratified sample is one where the sample reflects the population if there is an actual breakdown, if I actually know the breakdown of the population. So that's why you sometimes on the political, when they're giving you the statistics of an election and they'll break it down and say this percentage of this group voted this way and all that stuff, it's sometimes almost too much information. But if I know that a certain percentage of the population fits into a particular group, then I want to make sure that percentage of my sample is reflected. Otherwise, clearly, this sample here is a terrible sample. Men are way overrepresented on this sample when men don't even make up half the campus. Why would they make up most of the sample? Okay. Now, if it was absolutely random and I didn't even know if I was asking men or women, that's one way. So I'm randomly selecting people, but what I would do is once I hit 53 women, I would stop asking women, or once I hit 47 men, I would stop asking men if I'm randomly collecting. So let's break it down a little bit further now. Okay, I want to break this even further. I want a random sample of 100 students. There's not only 5,300 women and 4,700 men, but let's say that among the women, I'll keep it simple. 2,800 are 21 years old or over. 2,500 are under 21. I'll just write it like that. How's that? 2,800 are 21 and over. 2,500 of these women are under the age of 21. And among the men, there's 4,700 men. Let's say that 2,700 are 21 or over, and 2,000 are under the age of 21. Okay, so at Mesa College, for example, Mesa College, believe it or not, the student population is older than the student population, let's say at San Diego State. A lot of people don't realize that because at Mesa College, a lot of people come back to school. So a lot of times when we're doing things and we're trying to find out information at Mesa College, we will look at age breakdowns. So in my classes, the under the 21 are typically the people that are, they came right out of high school and went into Mesa College. There's a large group of people that do that. But some of the folks go off and work. Some of the folks go to the military. Some of the folks do other things, and then they come back to Mesa College. So there's a lot of classes where you have people that are much older in your class. And so at Mesa, we have an interesting breakdown. And a lot of times we use 21 as the line in the sand. It could be any number. So now at this particular college, I have 2,800 women who are 21 and older. I have 2,500 women who are 21 and younger. I still want my sample of size 100. But can I break it down further and even get more accuracy now that I know the age breakdowns? Okay, somebody walk me through what you think would be a really good way. Now remember, it's still got to be random, but I can certainly, distinguish. Now, I cannot walk up to you and know how old you are. That's not going to help. So let's suppose that I'm doing my sample and I'm sampling a woman. I will then say, how old are you? So I know which category this person falls in. That's very important. Because what if it turned out that the majority of my sample came from this group here? Well, no, once again, that would be overrepresenting. So with these numbers, does anybody want to try this? How should I conduct this random sample in terms of numbers?
Just keep asking people what age group they're in, and depending on the sex, just fill it in. And once you reach the percentage you want, stop.
Okay, so you're absolutely correct. So be more specific now. Give me exactly how many.
So say you're asking people and you're on the 27th woman that's over 21. The next one that was over 21 would be the last one you'd ask.
So you're saying exactly how many women over 21 should I be asking? Exactly how many?
28.
28. You notice I made the numbers really friendly on purpose here. So exactly how many women under 21 do I want to ask?
25.
And men?
27, 20.
So by the way, what you're describing is actually perfect because I need to get 53 women and 47 men. We all agree. But in my 53 women, I'd really like the breakdowns to be 28 in this age group, 25 in this group. Now, I can pretty much distinguish the men from the women, I would hope, but I can't distinguish the age group. So I'm saying, okay, how do you feel about this particular thing and how old are you? Once I've maxed out, I don't stop asking women, but I'm not going to count them in my poll if I've already maxed out on this category. And that's exactly correct. I don't say, sorry, I can't use you. You're too old. No, you don't do that. You just say, thank you. And you're keeping track. Once I've filled up that category, I no longer am going to include any more women over the age of 21. So I'm going to keep asking until I fill up this category. And that, by the way, that is exactly how you would do a stratified sample. You make sure that you have exactly that many in each category, but you still ask people. And when the category is filled up, you're done. You don't say, oh, I'm not going to ask that person. I made the numbers really, really, really friendly. If I didn't make the numbers friendly, then I need a calculator to figure out these. But this is still how it works. So now if you're thinking, I want to really get an accurate depiction of how people feel, then if I break it down into these age groups, boy, my sample is really going to be representative. Is it possible the sample's terrible? Sure. But the likelihood of a bad sample goes down and down and down as I improve upon these concepts. So a simple random sample, everybody's equally likely, and I'm not worried about who I'm collecting. But in real life, it is often the case that I really do need to make sure I don't overrepresent a particular group, okay? Overrepresentation also leads to underrepresentation. Has anybody been following what's going on in the NFL right now? Does anybody know what? Sort of like the hot button issue the last 2 days. I watch all the sports news too. Does anybody know what's going on right now? I'm just curious.
It's involving isn't it involving like it was like some dispute, like a legal fee, right?
Yeah. Brian Flores, the former coach of
Yeah.
the Dolphins, he's suing the NFL for exactly this sort of thing. That right now there's exactly one black coach in the NFL. One, Mike Tomlin of the Pittsburgh Steelers.
You're the head coach of this. Yeah.
How could there only be one? Yeah, one head coach. I'm sorry, one. How could there only be one? Well, there were two that were just recently fired, and he's talking about the underrepresentation in the interview process and the whole thing, significantly underrepresenting. And there's clearly bias going on here. Clearly bias. It's anybody who's just standing on the outside looking and going, that doesn't look right. How could the numbers be so different? Well, think of population, just in general, think of the population. If a certain percentage of the population fits into whatever category it is, could be male, female, could be ethnic, could be age, doesn't matter. If a certain percentage of the population fits into that mold, then everything in life really should look like that. If 60% of the country were women, then at every college campus, 60% of the students ought to be women. You'd think about it that way. Or, 60% of your employees ought to be women. It doesn't work that way always, but it's a starting point. Now, I'm not talking about fairness. I'm just saying representation. If you're trying to get accuracy, you can't over or represent any group if you're trying to give accurate results. Now, is there bias in sampling? Does that go on? Oh, yes. And does the news reporting of this do they sometimes make mistakes? Often they make mistakes. Being in California is such a disadvantage during elections. Does anybody know why being on the left coast can be real disadvantage? I'm talking about national elections.
We're majorly liberal.
No. I don't mean in terms of your politics. You're on the left coast.
Could it be, Professor, you're what?
I'm sorry, could it be what?
Could it be that? Go ahead, Lilia.
Oh, sorry.
That's okay.
No. I just said something out of the blue. Sorry.
Oh, go ahead, Rosalind. What do you think?
I was going to say, well, you're watching the elections before you had a chance to vote.
Exactly. Being on the left coast, we're 3 hours different from the East Coast. So what often happens during elections is we start hearing results from the other side of the country. Can that taint or affect your vote? Could it? I'm not saying will it, could it?
Yes.
Yeah, because you're saying, oh, so-and-so is already going to win. Why would I bother voting? Does that happen? Yes. Does that happen often? Yes. I can remember a particular election. I don't remember the year exactly. I want to say it was when George W. Bush was president. And again, I was driving home from campus, and I think I was heading towards the polling place. And I'm listening to the radio, and they gave results in 15 states on the East Coast. And they gave the winner, they said, the projected winner of those states. And they're announcing this to California voters. Now, the thing is, if they're announcing, and the best part about this announcement is 11 of the 15 states, they got it wrong. They announced the wrong person won that state because they did it too prematurely. The same news broadcast, I still remember this because my wife and I were watching the election results because I'm, presidential election, I'm interested in who won. Again, I can't remember, it was 2000 or 2004. George W. Bush was running against John Kerry. And it was a fairly close election. Around midnight, 12:30 at night, one of the news stations, one of the big ones, announced that John Kerry had won, and he's giving his acceptance speech on the news. By the way, John Kerry didn't win, and the final results weren't all that close. And the embarrassment of he's giving his acceptance speech. And about an hour or two later, they announced that George W. Bush had actually won, and by several million votes. And I remember thinking, I'm teaching statistics, how could they get it so wrong? How could you announce a winner that didn't win? Because what they were doing, they were using what they call exit polls. Now, an exit poll is when you go to a polling station. Now, a lot of you vote maybe in your neighborhoods. Okay, I vote in my neighborhood. There's always a house down the street where, you know, they have a little station in their garage. But some places, some people go to polling stations at really big places where everybody can vote. And so what the news was doing was they were asking people as they left the polling station, who did you vote for? I mean, that's a really simple question, and the person's going to tell you the truth. Now think about this logically. They're asking the person who's leaving who they voted for. And so they're collecting thousands and thousands of pieces of information this way. You say, how could they possibly get it wrong? Because in most of the states, the lazy pollsters, they sat outside the Democratic headquarters and asked the people leaving the Democratic headquarters who they voted for. That's kind of like going to Burger King and asking the people, are you a vegetarian, yes or no? People at Burger King are probably not vegetarians. People leaving the Democratic headquarters probably voted for the Democrat. I mean, I mentioned last day in, you know, the 1930, I think it was the 1932 election, when they called all the people and asked them who they voted for, and everybody voted for the Republican. That's because they only asked rich people who were Republicans. I mean, we can look at that now and laugh and say, how could they get this so wrong? Well, this is biased sampling. They did not have an equal representation, not even close. So if we're trying to collect data and we want, by the way, I don't want to measure 25,000 Mesa College students. My goodness. 100, I think we can do well. But if we're not careful in how we select our 100 Mesa College students, we could get a number that really isn't very close. Now, would that affect us in the long run? Well, it depends what it is we're measuring. I'm talking about average height of a Mesa College student, but there's a lot of other information. For example, there's things like income. The state looks at us and says, basically, are our students high income, medium income, low income? And depending on that sort of thing, the state may give us more money or may do other things. There's a lot of this kind of stuff that goes on. My wife teaches at a high school that is technically considered low income, although it's a very high achieving high school. And because of that, more money is provided for certain services. And that's really, really good for the students. Things like, for example, free lunch programs for a lot of the students because they wouldn't have it otherwise. But that's only because they have information, they have statistical data about family incomes, but they have to have all of the information correct and it has to be reported correctly. So if we're doing a poll at Mesa College and we are sloppy, right? We're being careless in our collection of data, we could end up having wrong conclusions made about our student body overall. And that could hurt us in the long run. So that's why data collection to do it right is so important. So now we're going to take a step back. There's something you want to perform. You're the head of your company, and maybe you're trying to market a new item. It could be something like I have a new item that I want to put on the store shelves. I want to know, do people like this item? Are they going to buy this item? How much should I charge for this item? How do I advertise this item? You want to get it right. There's a lot of money in this. So you have to collect the data. So what you do is you design the experiment. That's the terminology we use. We're not talking about a chemistry lab experiment, but you design the experiment. You have people collect the data. Now, after the data is collected, the numbers are, we'll call it crunched, right? I'm getting out my calculator, I'm crunching the numbers, and then at some point there's a conclusion that I'm going to make. There's a whole sequence of things, but the data collection is critical because all statisticians, if I give you the data, all statisticians are going to come to the same conclusion because they're going to use the same mathematics on this set of numbers. It's the data collection then that is so extremely important, okay? I could be doing something where maybe I'm testing ocean water. I'm testing it for its salt levels, whatever. Well, if I'm careless in my data collection, I could get the wrong conclusion at the end. So I have to collect data correctly and I have to analyze it correctly. So when we're talking about something as simple as a sample, I have a sample and I want to get it right. I want to make sure that whatever outcome I report, it is accurate. Now, I'm collecting data and I did this problem, but is it still possible the people I asked we're not a great representation of this student population? Is that still a possibility, folks? I asked 28 women randomly over the age of 21, but is it possible that those people, you know, were leaning in one direction far more than another group might have been?
Yes.
It's always possible. Is it highly likely? Here's another way of looking at this. Each one of us are going to go to this campus and do this particular sample, and doesn't matter what the question is. The question could be, how many units are you carrying? The question is, how many children do you have? The question might be, how much money did you make last year? The question is, did you vote for so-and-so? It doesn't even matter what the question is. Every one of us are going to go to this particular campus. Every one of us are going to do this stratified sample, and every one of us is going to collect our data. Is every one of us going to have exactly the same outcome, do you think? Are we all going to have exactly the same results? Anybody want to try that one?
No.
Probably not. In fact, it's probably reasonable to say that every one of us is going to have a different result. But are our results going to be extremely different, or might they be fairly close together?
They
But
should
what do you
be,
think is more reasonable?
they should be pretty close together.
Yeah, realistically, all of us should come up with different conclusions because we did not ask the same people, but we did the sampling the same way. So in the end, my result said, well, maybe it's income. The average income of a student of this campus is this. And then your result is, well, I came up with this number and somebody else came up with a different number. But when we look at all of our numbers, we'll say, you know, they're not all that far apart. That is a reasonable outcome. Okay, that's why the bigger the sample, the better things are. Now, there's mathematics that prove that part, and I'm going to do that later. I'm not going to hold you guys to that because that's a calculus kind of thing. We don't need to do that to understand. So the idea is, the first part of today's class is, how do you collect a sample that is representative? If you want to use the word fair, great. Unbiased is a more statistical word. I want to have a sample that is reflective of whatever my population is. So any conclusions that I make, I can trust that I did it right. If I don't trust that my sample was unbiased, then the results are they're irrelevant. It's not even important. It's not going to be perfect, but it's a start. The more care I give to making sure my sample is unbiased, the more likely the results are very close to what the real results are. Whatever the 10,000 students actually think, if I did the sample well, the results of the 100 people I ask will be very reflective of the entire campus. And that is the hope when you're doing a sample. All right, let's take a short break. When we come back, we're going to look at different stuff involving the data. So I'm going to pause right now. All right, we're going to do something after we've collected the data. Putting the data into convenient groups or clusters is a very important thing. So we're going to look at what is called a frequency distribution. Now, a frequency distribution, frequency is how many times something occurred. So I want to start with something really simple like a die or a coin flip. And what I want you to do is you need a pencil and paper in front of you. I want you to roll the die and write down the result. And I want you to do this 20 times, just 20. I mean, we could do it 100 times, but that would be time consuming. So roll the die, whatever it is, it's a 6, put 6. And then just write down 20 times. Coin flip, flip the coin 20 times and write down head or tail, H or T. Keep it really simple, okay? So I want everybody to do this, write down the results. Again, it shouldn't take more than a minute, but write down the results. So it should be a sequence of 20 things, either the numbers 1 through 6 or H's and T's. Okay, so let's all do that. Okay, I'm going to do it myself too. Okay, let me know when you're done. Okay. Okay. These are our choices. If you have a die, the number on the die, 1 through 6, F is frequency. How many times did it occur? If it's a coin, the face of the coin is the head or the tail? And then how many times did it occur? So what I'd like you to do, depending on which one you did, make a little picture like I did. Now you've got 20 things. Just count them up. How many ones? Do the ones first. How many twos? How many threes? Heads and tails. How many H's? How many T's? So the counting should be really simple. Okay. So I'll show you what I got for mine. This is what I got for mine. Now somebody else, if they're doing H's and T's, who did a coin?
I did the coin.
Okay.
I did.
Okay, Robert, how many heads did you get?
10.
You got exactly 10?
Yeah.
Wow. Did anybody get not 10? That'd actually be unusual. Did anybody get a different number for their heads and tails?
I got 7 heads and 3 tails.
But 20 flips?
Oh, I did 10 flips.
Okay, so I wanted you to do 20 is just because it's a little more information.
Oh,
Did anybody-
exactly.
Yeah. In other words, one of the things that kind of should, those numbers have to add up to how many times you did it. That's why I said do it 20 times. So a little more information. Now, there's no right answer. There's no wrong answer. If I flip a coin 20 times, by the way, am I going to get 10 of each? That's the most likely, but am I going? Did anybody else do a coin?
Yes, I did, Professor.
How many heads did you get?
15 and 5. 15 heads, 5
Mm.
tails.
You-
Maybe
now-
it's because
now
of my
you-
nails.
I did a coin
I
too.
don't know.
Now, see, this is what's great about this. You start going, is that a fair coin? We're going to discuss the mathematics of a fair coin later. I'm not interested in whether your coin is fair or not. I'm interested in how do we do this count? This is what I have here are called frequency distributions. Frequency is how many times it occurred, and these are all the possible outcomes. And so at the end, it's kind of got to add up to the number of what we call the number of trials. So I rolled a die 20 times. Now 20 divided by 6 is 3 1/3, but I can't get 3 1/3 for each of these. That's really not realistic. 20 divided by 2 is 10. You could get 10 for each. Most people would probably, 11 and 9 or 12 and 8. There's no right or wrong answer. But what I'm doing is I'm doing a count so I can see things. We're going to be drawing pictures next day. Yeah, actually graphical representations of this sort of thing. Right now, we just want to do the count. So there's a couple things about a frequency distribution. First of all, you have to have all the outcomes available, and then the frequency of each of the outcomes. So it's something as simple as rolling the die. You can see my outcomes. I did not get the same number each time. There's by the way, when I do this again and again and again, I probably see a different set of numbers every time. That's okay. I'm not worried about that part. It's right now just the collection of the data. So I have it like this. Now, what if this was, let me change it. Now let's say this is income, and maybe it's income of Mesa College students. We have a really big group of people. So let's say we have 25,000. When I do income, do you think it would be practical to list, starting with $0 and then 1 cent and then 2 cents and then 3 cents, all the way up to however many millions of dollars? Okay. Do you think it would be practical to put every single income of 25,000 people on a chart?
No, sir.
Yeah, really touch them. What might be more, I don't know, what might be easier for me to work with and see it rather than putting every single conceivable value? Well, think like taxes. There are tax brackets, aren't there? If you made between this and this, if you made between this and this, if you made between this and this. Would income maybe everybody from 0 to 10,000, and then everybody from 10 to 20,000, and then everyone from 20 to 30. Might that be a little more convenient if I did something like that?
Yes.
Yeah, fewer groups. And then if you made between 10 and 20,000, there's a lot of incomes between 10 and 20,000, right? You know, $13,468.18, you know, and then somebody else. But if I did it in groups of numbers, then it'd be a heck of a lot easier to keep track of. Plus visually, I'd say, okay, everybody in this group, everybody in this group. You see, if we're talking about income, there's just too many options. Now, what about something like test scores? I like to make exams worth a lot. And what I mean by a lot, in my calculus classes, my exams are worth 600 points. You say, that's so much. Well, no, because the course is worth like, 2,500 points. I like to make exams worth a lot. That way, when a student makes a small error, they're going to be a deduction because they made an error. But on a 30-point problem, I can take off 1 point. If I made that problem worth 5 points and they make an error and I take off 1 point, 1 point from 5 is far more damaging than 1 point from 30. Hopefully you see the logic in that. I like to make the exams worth a lot, so then errors can be really small deductions rather than huge deductions. I had a friend who gave calculus tests and they made every problem worth 4 points. They rarely had anything higher than a C, because if a person made a small error, they lost a point. So that means they now have 75%. I gave the same test and I made that problem worth 40 points and I took off 1 point. Now that's an A+. So I'm going to give an exam. In our class, I think our exams are 400 points. So same thing. Am I going to put, okay, you got a 0 or a 1 or a 2 or a 3 all the way up to 400? That kind of looks like the income example, doesn't it? Too many possibilities. Oh, but wait a minute. Don't we usually group things by, think letter grades? Oh, so if I gave a 400-point exam, why don't I group it to the scores that were A's and the scores that are B's and the scores that are C's? But aren't there a lot of scores that can be an A and a lot of scores that can be a B? Right? Same sort of breakdown. That would make more sense rather than every individual value. So why did I do it here? Because there's only 6 possible numbers on the die. There's only 2 possible values on the coin flip. But the exam scores or the income, there's way too many possibilities. So now we start doing it in groups of numbers. So let me give you an example. Okay. So let's suppose that we had an exam, and we'll keep it simple. We'll say we gave 100-point exam. We'll just keep the number simple. We gave 100-point exam and we did it to, let's say, I don't want this to be unrealistic. Let's say 30 students. And here were the scores. And I'm going to have them sorted. I got 100 and a 98 and a 97 and a 96 and a 94 and a 92 and an 89 and an 88 and another 88 and an 86. And an 84, and 83, and an 80, and a 79, and a 77. There was a 75, another 75, a 73, a 71, a 70, another 70, a 68, 1, 2, 3, 4, almost there, 67, 64, 61, 60, 59, 57, 55, and let's say finally, how about 51? All right. So there are 3, 4, 5, 6. There are 30 scores, and these are sorted. Now, a lot of folks will say, well, if I have the scores, won't they just be randomly? Yes, but sorting is actually one of the simplest things that any computer can do. I mean, when I'm doing my stuff, I'm doing my taxes, I'm entering scores. I have a little icon up there that just says sort. I can sort things alphabetically. I can sort things numerically, and it's literally instantaneous. I could have 1,000 numbers and I hit sort and they're all sorted. So never worry about, oh gosh, I got to put everything in order. Any technology will do that. So I'm always going to start with things that are already sorted. So I've got a group of test scores, and now I want to report the frequency distribution. So when I do that, here's the question. Should I make my table start at, the number 1 and go all the way up to 100 and then put, well, I don't have a lot of repeated scores. That probably wouldn't be as wise. Rather, maybe I break it down by groups of numbers, okay? So if you think about, in that case, groups of numbers might make more sense. So one of the ways we want to do it is when I do groups of numbers. Now tell me, if we were doing income, I'll keep it simple. If we were doing income, would it make sense to do something like this? All right, I have 0 to 10,000 will be one group. 10,001 to 100,000 will be the next group. 100,001 to 1,000,000 will be the next group. And then maybe 1,000,000 plus will be the next group. Do you think this would be really, really a good way of doing this? Would this be very accurate?
No.
What don't you like?
There's a huge gap between each number given.
Yeah, this group has basically 0 to 10,000 means this group is 10,000 incomes, but this is 90,000 incomes. This is 900,000 different incomes. In other words, in my individual groups, there's only a 10,000 difference here, but there's a 90,000 difference here. There's a 900,000 difference here. Wouldn't it make sense that the gaps were equal all the way down? Wouldn't that make more sense?
Yes, they should be at the same interval.
So if this is 10, then the next one probably should have been 10 to 20 and then 20 to 30 and 30 to 40. But if you're saying, well, there's too many, then just simply make them bigger. So would it make any sense for me to group my numbers? Well, I'm going to have all the numbers between 95 and 100, then between 60 and 95, and then between 0 and 60. Well, no, I mean, those gaps ought to be really equal. So how do I decide? Really, the easiest way to do it is look at the high and the low. Look at the high and the low and say, how far apart are these? There's about a gap of 50. So maybe every 10 scores would be a logical way of doing this. Okay, so this is not a right or wrong answer, but maybe when I'm sectioning these off, maybe I do it by grades. That's probably the easiest one. So maybe one of my groups would be, maybe I want to do this: 90 to 100, 80 to 89, 70 to 79, 60 to 69, 50 to 59. Now, I don't have anything below 50, so I don't need to keep going. First of all, does this seem reasonable as a starting point for my different groups? Anybody?
Yes.
Yeah, because they're all 10 apart. So let me put score frequency, okay? When you're looking at this set of numbers, I don't know, when I'm looking at that many numbers at once, to me, it's kind of like the Matrix movie, all the computer screen. Everybody know what I'm talking about? The green numbers that are always going up and down, and you see billions and billions and billions of symbols. You guys know what I'm talking about?
Yeah, like the data and all that.
Yeah, the Matrix, it's just like, it's too much information. Everything we need is right here, but I gave you 30 numbers. What if I had 1,000 numbers? It's too much information. I can't look at this and tell what's going on. It's overwhelming, even though there's only 30. But if I break it down into groups, it's much, much easier for me to interpret really quickly what's going on. So let's go through here. 90 to 100. Let me put a little, okay. And then 80 to 89. Okay, right about there. And then 70 to 79. 60 to 69. I'll make it easy on myself. I'm just going to count. All right, so I have 1, 2, 3, 4, 5, 6 numbers in this group. I have 1, 2, 3, 4, 5, 6, 7 numbers in this group. 1, 2, 3, 4, 5, 6, 7, 8 numbers in this group. 1, 2, 3, 4, 5 numbers in this group. and 1, 2, 3, 4 numbers in this group. And by the way, always add your frequencies. It's 13, 21, 30. Why do I do that? Because I have 30 scores. My frequency kind of has to be 30. I may have miscounted. I may have one of the numbers off. So that's why I always double check. Now, if we decided to call these letter grades, what are we saying? 6 A's, 7 B's, 8 C's, 5 B, 4 F's. Do you have a really quick interpretation now of how this group did by looking at these numbers? Probably. In fact, it's probably easier for you to look at these. Hey, by the way, look at more scores were C's than anything else. And the numbers kind of make sense. They go down in each direction. But I gave you a bunch of numbers. You created a frequency distribution. The frequency distribution is a summary, right? Because we didn't put every single score, we grouped them. Income would be another thing. Housing costs would be another thing, because there's too many different prices you could pay for a house. So you'd say everything between here and here. There's too many different individual incomes. So you'd say all incomes between here and here. And in this case, all test scores between here and here. It would just make a heck of a lot more sense. So a frequency distribution, there's two things I can do. When I did the coin flip and the roll of the die, I listed every outcome because there weren't that many. When there's too many outcomes to list every outcome, then you group them and then you count them. But when you group them, it's very important that your groups are basically the same width. I wouldn't say 80 to 100 and then the score of 79 and then 0 to 78. I mean, that's kind of extreme, right? You want them all to be roughly the same. Now, income brackets, housing costs, big difference is I gave a 100-point exam. I have a highest score, don't I? 100 would be the highest score. What would be the lowest possible score?
50, 59.
No, the lowest possible score would be
Oh,
0.
0.
So do you agree there's a range that's set before I even start? I can't exceed 100, I can't exceed 0. Income. Is there a lowest income? Yeah, 0, you didn't work. Is there a highest income? Is there an income that is the
No,
highest
there
any human
shouldn't.
being can achieve? No, there's no upper limit, is there? No matter how much money somebody made, somebody could have always made more. Oh, so that's, we say it's open-ended. How about housing? Housing costs. I can look up online what every house in San Diego sold for recently. That's information that's right there. Is there a highest cost a house can sell for? Is there a highest number?
Yes.
Are you sure? Not what's the most somebody did sell for, but is there a number that no house can be higher than this, or could it always go up?
It can always go up.
It can always go up. So the most expensive house that sold last year, this year somebody will spend more. Somebody will sell for more. So the two areas, and I will use these often, the two areas that are always open-ended are income and housing, because there's no highest number a person can achieve. Now, I'm a big sports fan, and I kind of wish I had been born a professional athlete. That would have been great, because professional athletes, well, they have unlimited income opportunities. That's not why I would want it. I would want to do it because I want to be Tom Brady, right? Is there a highest income a professional athlete can have? No, because we always know this, but we'll use quarterbacks for an example. The next quarterback who has to negotiate his contract will be the new highest paid quarterback. That's always how it seems to work. But that number always is moving up. There's no line that says, okay, that's it. Nobody can go past this. Now, you have the score of a game, right? I'm watching the Laker game last night. When the game started, I could predict the score when the game started. I already knew what the score was going to be when the game started. 0-0. Now, it wasn't going to end 0-0. Is there a highest number of points a team could have scored in the basketball game? Is there a highest number?
Yes.
Really? Are you sure?
No.
If you give me that highest number, what if they make one more basket? So again, same thing. The score of a game, think about that. The score of a game, there's no highest number. Now, there may be a highest number that somebody has gotten so far, but before the next game, see, I'm a big hockey fan, and I was watching the Kings game yesterday, and I thought the game was over. They were up 4-3, and then they got an empty net goal in the last couple seconds to get 5. Well, what if they got one more goal? Then they would have had 6. Is there a highest number of goals they could have gotten? Nope. So anything that is open-ended, this is where it gets a little tricky. You notice what I did with the income. Now, these are terrible brackets, but you notice in the last group, what did we say? Everybody who makes over $1 million. We don't cap the income. We usually just say the highest income bracket. Now think taxes. All right, we're in February, and you probably have gotten your W-2s from last year by now, and probably a lot of you got to start thinking about doing your taxes or getting them done by someone else. So when you look at the tax brackets, the lowest bracket starts at $0 and goes up to a certain number. I don't know what that number is. Maybe it's $10,000. And then you have each bracket. The last bracket will have a number. And again, I haven't looked at it in a while because I have my taxes done. Maybe the last bracket starts at $100,000, but it will basically be 100,000 plus. It doesn't say 100,000 up to this highest income. It will just simply say plus. Because now every income over that, regardless of how high it is, will now be in that tax bracket, because the last tax bracket doesn't have a highest number. So I can't do income brackets the same as I could do test scores, because we agree there was a highest possible test score. There was also a lowest possible test score. Nobody got it, but there was a lowest score. Income has a lowest income, 0, but it has no highest income. So I can't cap it with this. Now, we could always say, well, what's the most a person made last year? But that doesn't mean that would apply to this year, because somebody could always do better. Okay, so this is, when you're doing a frequency distribution, it's actually quite simple. But the problem is creating these sometimes can be a little bit tricky. So the next thing I want to show you, oh, keep losing my, okay. When we are doing this, there is no score between 89 and 90. There is no score between 79 and 80. There is no score between 69 and 70, and so on. So often it's the case in a frequency distribution that we change these edge numbers so that these are the same number exactly. Now, I'm going to give you an example with sports. Okay, and if you ever pay attention to sports and you watch things like this, you kind of understand. Now, there's a Super Bowl coming up, and there's going to be a lot of people betting on the Super Bowl. We're not going to talk about how to gamble on the Super Bowl, but there's going to be a lot of people betting. And so the casinos and whoever's in charge, they set what's called the line. They'll say who is the favorite and by how many points. So when you bet, you're not necessarily betting on the team, you're betting on what's called a point spread. Now, I'll give you a really simple example. The casino might say the Los Angeles Rams are favored by 3 points. That's kind of like saying that to make the game fair, we're going to give the Cincinnati Bengals 3 points to start with. You're going to start ahead 3-0, and then the rest of the game will be even. And then if the Rams win by exactly 3 points, right, then we're saying it's exactly what we said. But if you bet on the Rams, you won't win if they win by exactly 3. If you bet on the Bengals to lose by exactly 3, you won't win. The casino will actually win if it is exactly 3. This is kind of confusing. So usually when you see a point spread, you don't see the Rams are favored by 3. Does anybody know what they might say in the point spread? It's kind of crazy. They're favored by anybody? Not by 3. By 3 and a half. Does anybody ever hear point spreads like that? 3.5.
It's like I've heard it before, but barely.
And by the way, this is most of the time. I'm watching things because I watch sports networks a lot, and they'll say, you know, the over under, that's, you know, how many combined points, or the Kings Detroit game last night, the over under on goals will be 5.5. Well, you can't have a half of a goal. That's why they do it. So if the Rams are favored by 3.5 points, by 3.5, oh, then if the Rams win by 3, a group of people will win their bet. But if they're 3 or less, if the Rams win by 4 or more, the people will win their bet. Usually in sports, when they pick those winners, they pick a score that's halfway between two possible scores, because that way there will always be a winner and a loser of the bet. So let's suppose we're betting on coin flips, and we flip the coin 20 times and there was 10 heads and 10 tails, and I'm picking heads, you're picking tails, and there was exactly 10 of each. Well, then neither one of us wins. Only if one of us had more than the other would one win. So when it comes to sports in general and gambling, a lot of times it's an impossible outcome is where the line in the sand is drawn. Therefore, the result has to be on one side, the result has to be on the other. It's that simple. So we're going to do a coin flip game, and we're going to make it, you're going to do the 20 flip coin flip. And we'll say 10.5 is the number of predicted heads. So if it's more than 10.5, you win. If it's less than 10.5, I win. Well, since you can't get 10.5 exactly, there will be a winner. But if we said it's exactly 10 and then it comes out 10, we end up in a tie, nobody wins. That's confusing. So what we often do on here, instead of 90 and 89, we'll make this 89.5. And we'll make this one 89.5. Because nobody can get 89.5. You're either above 89.5 or you're below 89.5. But we make the last number here the same as the first number here. And I'm going to show you why we do that in general, because sometimes it makes the graphical representations much, much simpler. And there's other things that go on. So a lot of times we'll change this to 79.5 to 89.5. 69.5 to 79.5, and so on. And we'll do it that way. Every single outcome will fall into a category, but then there's no gaps between the categories. Okay. There's some logic to this. We're going to go over that kind of stuff a little bit next day about how to do this. Okay. I'm going to stop now because there's not a whole lot of mathematics necessary to understand this. We're going to do some more of this next day. So